Hi, in this lecture, we will be discussing about hypothesis testing about mean and proportion. In particular, hypothesis testing about one sample. So for this part of the lecture, we will be discussing about what are the two hypotheses involved, the rejection and the non-rejection regions, what are the types of errors, and what does a two-tailed or a one-tailed test mean. So by definition, we actually have two hypotheses. So the first one is the null hypothesis, and it is defined as a claim or a statement about a population parameter that is assumed to be true until it is declared false. So basically, the null hypothesis is the de facto working hypothesis that we have. And it's called null hypothesis because it always says that there is no significant difference. So that's why it's called null. And we also have the alternative hypothesis. The alternative one is the claim about a population that will be declared true if the null hypothesis is declared to be false. So it's called the alternative because if the null hypothesis is false, it becomes our we conclude about the alternative hypothesis. So we have here what you call a rejection and non-rejection regions. So it's called a region because usually when we look it up in the normal distribution curve, it's basically the area beneath a certain curve. Starting from a certain point. So basically, we have a non-rejection region that describes the region where, for example, here is as an illustration, we have a court case about a certain whether it's guilty or not. So if it's there's not enough evidence to declare a person guilty, and basically this is a non-rejection region. So there is no guilt found. This is just an illustration, a sample illustration as applied in certain court cases. So person is not there is not enough evidence that shows that a person is not guilty. That is the non-rejection region. And then we have the rejection region, whereas there is enough evidence to show that the person is guilty. So basically, for a null hypothesis, the norm for the null hypothesis is that there is always no significant difference, or there is always not guilty. Basically, the premise is innocent until proven guilty. So you're always working on the assumption, or the working hypothesis rather, is that it's not guilty. So you want to have uh, basically you are working on finding enough evidence to declare the person guilty if you really want or rather that's a different way. The de facto or the automatic assumption, or the automatic working um, the automatic working hypothesis that we have is it's not guilty. So this is the non-rejection region. So statistically, we need to find enough evidence to declare a person guilty in order to go from the non-rejection region to the rejection region. So basically that's that. So we always start here at the non-rejection region until we find enough evidence to go to the rejection region. So basically, that's actually the de facto norm, not only in court case but also in statistical hypothesis testing. And by the way, this is now not no longer descriptive statistics. This is now the inferential statistics, where we conclude about a certain means and populations parameter. So there are four possible outcomes for a court case. It's not limited to whether you're guilty or not guilty. There's actually four. So we have, and that four outcome is based on the court's decision and the actual truth. Because of course, sometimes court decisions as a human establishment, they can also have errors. They can also commit errors. So basically, when you have the actual situation, which is the truth, versus the decision of the court, or basically from if you're in the statistics, if you're if in the point of view of yourself as the investigator, your decision whether it's true, whether you should accept or not accept the null hypothesis. So anyway, so if your decision or the court's decision is that the person is not guilty, and the actual truth is the person is really not guilty, so basically that's a correct decision. But if the court decided, or you decided, that the null hypothesis is not to be rejected, there's no significant difference, the person is not guilty according to the court decision. However, what in reality is that the person is actually guilty. You just haven't found enough evidence. That is basically a type 2 error or a beta error, which is basically a false negative. So you assume that it is not guilty, there is no significant difference, but in reality, he is guilty. So it's a false negative. And then you have, if you the decision, your decision is the null hypothesis should be rejected, or in this case, the court's decision is that the person is guilty. But in reality, the person is not guilty. You have committed what you call a type 1 error, or an alpha error. And lastly, and the last outcome is that if the person is guilty and you have found that person to be guilty, so for example, in your investigation, there is a significant difference, and there really is a significant difference, which is the actual truth. That's a correct decision. So the four possible outcomes here, two of them can be correct decisions, and two of them are erroneous. So one of them, this type 2 error, is a false negative, and this is a false positive. Whereas you assume it's guilty, but it's really not, so it's a false positives. So these are the four possible outcomes that you have. And basically, we need to have robust statistical tests in order to prevent committing these type 1 and type 2 errors. So let's look at these errors closely. So by definition, a type 1 error occurs when a null hypothesis is rejected. So we have here the value alpha. You have seen alpha in our previous lectures. Basically, it's the significance level of our confidence level, basically. So the value alpha represents a probability of committing a type of error. So we usually have 1 minus alpha percent as the significance as our confidence level. For example, we are 95% confident that that the mean is within a certain interval that we have, and we do have and that 95% is defined as 1 minus alpha. Therefore, alpha is 5%. And that 5% represents the possibility that we might be wrong in our assumption, or in our, basically, statistical analysis. Now, the alpha is the significance level of the test, where it tells us how probable are we to commit a type 1 error. How probable are we to actually have a false positive, to declare something as a guilty or a significant, but it's really not significant. So remember, person is not guilty, but you reject the null hypothesis and declared a person as guilty. So what is the probability of us rejecting the null hypothesis when it should not be rejected? That's a type 1 error, or the alpha, which is a numerical representation of how probable are we going to commit that error. And then we have the type 2 error. So the type 2 error occurs when a false null hypothesis is not rejected. So it's the opposite situation as the type 1. In type 1, we reject the null hypothesis, whereas we should not reject it. In this case, we do not reject the null hypothesis, but however, in reality, we should have rejected it. And it's represented by a value of b, or rather beta. The beta represents the probability of committing a type 2 error. So the 1 minus beta is the power of your test. So it represents the probability of not making a type 1 error. So if 1 minus alpha percent is our confidence level, the 1 minus beta is the power of your test. So it tells us how probable are we to not make the type 2 error. So basically, these are another look at this situation. This is no longer represented as a court case, but rather our decision whether we reject or accept the null hypothesis. So we have here the decision. If our decision is not reject the null hypothesis, however, the null hypothesis is actually false, and that is now our type 2, or the beta error. And when we reject the null hypothesis, whereas the null hypothesis is actually true, that's a type 1 or an alpha error. Now let's look at the tails of a test. So we have a two-tailed test. where basically when you look at this is based on how you look at the normal distribution curve. So when you have a two-tailed test, you have rejection regions on both tails, on the leftmost side and the rightmost side of your normal curve, distribution curve. And then we have a left tail test. The rejection region is only on the left tail, and the right tail test, the rejection region is only on the right tail of your distribution curve. So let's look at an example here for how do you know if it's a certain hypothesis testing should be two-tailed or a one-tailed test. So let's have this example. So according to the U.S. Bureau of Labor Statistics, workers in the United States who were employed earned an average of $50,400 a year in 2019. Suppose an economist wants to check whether this mean has changed since 2019. Now, when the question here is it changed? Is it different? That's basically a two-tailed test because it doesn't say that it should be greater or less, but rather, is it changed from the value? So that is a two-tailed test. So another example here, the mean annual earnings of employed Americans has changed if it has either increased or decreased since 2019. So again, whether increase or decrease, if you're checking whether both increase or decrease, it's a two-tailed test. So here is the hypothesis, the null and alternative hypothesis for the first example. So first, the null hypothesis is that there is no significant difference. So mu is equal to 50,400. So the mean annual earnings of employed Americans has not changed. So the null hypothesis always says that there is no significant difference. And the alternative is, of course, that it has changed. There is a significant difference. So whether a test is two-tailed or one-tailed is determined by the sign of your alternative hypothesis. So basically, since the null hypothesis always said there's no significant difference, it really doesn't tell us what will be the tail of the test. The tail of the test we will give an idea of that based on our alternative. If it's not equal to, that's a two-tailed test because it checks whether it increase or decrease either ways. As long as it change, that's a two-tailed test. So if it's here is the representation of the tails. So again, the rejection region is on the extreme ends. So this is the rejection region. Since it's a two-tailed test, the rejection region is divided between the both sides of your normal distribution curve. And the point that separates the rejection region and the non-rejection region is your critical values that we are looking for in order to whether reject or accept our null hypothesis. But more on that later. Okay, how about left tail test? So, reconsider the example of the mean amount of soda in all soft drink cans produced by a company. So, the company claims that these cans, on average, contains 12 ounces of soda. However, if these cans contain less than the claimed amount of soda, then the company can be accused of cheating. So, suppose a consumer agency want to test whether the mean amount of soda per can is less than 12 ounces. So, it's just looking for if it's less than 12. It's greater than 12, it doesn't really matter, as long as it's not less than 12. So, the fact that it has a direction, it must be less than. It's not must be equal to, but rather it must not be less than 12. It indicates a handedness, or basically you have a left tail or a right tail test. So if it's less than, so the alternative hypothesis is that mu is less than 12 ounces. So if it's less than, it's on the left side. So basically, the rejection region is only on one side, and that is on the left side. If you notice, the region here is actually significantly larger than when in the two-tailed. Because in the two-tailed test, the region is divided, the shaded or the rejection region is divided between the two tails. However, for a left-tailed test, you are only concerned whether it's less than your mean. And that is concentrated on one side, and that is why it looks actually a larger area, because the whole alpha is not divided into two, but the whole alpha is concentrated on the left side. So this is your rejection region for a left tail test. And then for a right tail test, if the left tail is for the less than assumption, the right tail is for the greater than or higher than assumption. So for example, according to an estimate, the average price of detached homes in Newark, New Jersey was $321,257 in 2019. Suppose a real estate researcher wants to check whether the current mean price of homes in this town is higher than 321,257. So if it's higher than, it becomes a right tail test. So it's a greater than the alternative hypothesis has a greater than amount and it becomes a right-tailed test. So the alternative hypothesis greater than, so it's a right-tailed test. So same approach as the left-tailed, only on the opposite side. It's on the rejection region is on the right side of your, and the critical value separates the rejection and the non-rejection region. Okay, and so far that's it for your testing. Actually, this is the summary of the tails of the test. So your null hypothesis is always equal. This is equal or greater than, because for a left tail test, it can be greater than or equal, because we don't really we are not interested on being greater than. We are only interested if it's less than. And on the right tail, we are only interested if it's greater than. We are not really interested if it's less than. So whether it's equal or less, and it's not an issue for the null hypothesis. So the alternative hypothesis here for both tails is not equal to. If it's in the left tail, it must be less than, and if it's in the right, it must be greater than. So that's it for the tails of the test, and in the next part, we will talk about how to make hypothesis testing.